Hello and welcome. This is New England Dynamics and Number Theory again. And today our speaker is from far away, from Tel Aviv, Israel. We're happy to see and hear Alon Agin from Tel Aviv University. And the title is The Dirichlet Spectrum. Thank you, Alon, and please welcome.
Okay, so I'll start obviously with thanking you for the invitation. I'll say that this is based on a work of myself and Barak, which is a part of my PhD thesis. And I'm assuming that the talk will be something like 45 minutes. Please, yes, you have something to say?
It's up to you. We can take longer or we can ask questions afterwards.
Yes. So before the discussion afterwards, it will be something like 45 minutes. But also feel very free to stop me at any time. If you have questions, just stop me. Okay, so I'll start with the introduction. So throughout the talk, we're going to have a norm on Rm and a norm on Rn, and I'm going to denote them in the following way. Don't be confused with the p-norms. The letter at the bottom is just to indicate the dimension. So firstly, I want to recall the Dirichlet theorem, but the higher dimensional generalization of it, which states the following. It states that there exists a minimal constant. I'm going to denote it as delta. Delta is dependent on the two norms that we have, and I'm going to use this symbol in order to specify a dependency on both norms. This is a bit of a weird way to specify this dependency, but it will be a bit understood later on. So there exists a minimum constant delta such that for every t sufficiently large and any matrix with m rows and columns, there exists q and p integer vectors such that these two equations holds. I'm assuming that the audience are familiar with the Dirichlet theorem, but I'll just, in case maybe someone in the audience are not that familiar with this generalization of it, I'll just say that the idea of this theorem is that we want to give a good rational approximation of the matrix theta, meaning that we want to know that this quantity is small, with compare to the size of the what we call as the denominators. The denominators are the q's. So this is the theorem, and the motivation for the start of the motivation for the talk is, let's assume that we have a fixed matrix. So can we improve the upper bound delta given to us by the Dirichlet theorem for this specific theta? Okay. So in order to address this question, we do the following. For a matrix theta and for t large enough, we define the rescaled irrationality measure function, which is dependent on both norms, to be the following function. We denote it by chi, and chi is a chi of theta t is t to the power n divided by m, where we multiply by the best rational approximation that we get for theta, where we only allow q to be with length at most t. So let's state the Dirichlet theorem with respect to this function. It's just saying that for every t sufficiently large and any matrix, we have that the rescaled irrationality measure function is always get some value between 0 and delta. And now, before I move on, I do want to say that all objects that we're going to discuss today are very, very norm sensitive, and they are norm dependent. I'm only going to denote this dependency once. Let's say in here when I define the object, and then I don't want to have like messy notations. So just keep in mind all the time that everything is dependent on the norm that we work with. And now for a fixed matrix, we define the Dirichlet constant of this matrix to be the lim sup of the irrationality measure function. So obviously, by Dirichlet theorem, we have that for any matrix, this constant is some number between 0 and delta. And furthermore, this Dirichlet constant is the infimum over all constants, which enables us to improve Dirichlet theorem for this specific theta, meaning enables us to replace delta with a smaller upper bound in the previous two equations. Let's discuss some obvious observations. So firstly, if we have a rational matrix, then of course that this value becomes 0 for t large enough. Hence, the lim sup is 0 and the Dirichlet constant is 0. Where in this case, we say that if the Dirichlet constant of a matrix is equal to 0, we say that theta is singular. This is maybe a definition that you're familiar with in a bit of a different definitions. And the typical case, this was a famous result by Davenport and Schmidt from 1970, stating that for Lebesgue almost every theta, we have that the Dirichlet constant of it is actually equal to this upper bound delta. They proved it actually for a specific case, a specific dimensions and specific and the maximum norm, but their method can be generalized to this generalized settings. So the question is what happens in the non-typical case? And in order to address this, we define the Dirichlet spectrum of the space of matrices, again, with respect to the two norms that we have, to be just all values of Dirichlet constant, where we allow theta to vary in the space of matrices. And clearly, the Dirichlet spectrum is just some kind of a subset of numbers between 0 and delta. And for the case of n equals m equals 1, this is the classical case, the classical Dirichlet theorem. So mostly by using continued fractions, we know that the spectrum of 1, 1, in here we have only the absolute value. We don't even need to specify the norms. And we know that this has a complicated structure. In particular, we know that it is not the segment 0 to gamma. In this case, gamma is the number 1. And furthermore, we know that there exists some r greater than 0, such that the interval 0 to r is completely outside of the spectrum. And this was done by many results in many years. And let's discuss some recent results. So the most breakthrough paper to this object was 12 years ago by Akhunzhanov and Shatskov, where they showed that for the specific case of m equals to 2, n equals to 1, and for the Euclidean norm on R2, we have that the Dirichlet spectrum of these specific settings actually has a very different behavior than the 1, 1 case. And it is the whole segment between 0 and delta, where delta in this case is this number. And this was a very surprising result because it is very different than what happens in the 1, 1 case. Then for some time, as far as I know, there hasn't been many results which were connected to this object, but in recent years, many results came out. So I'm only going to discuss some of them. So firstly, 3 years ago, Dimitri and Anor Agrau showed that for m equals 2, n equal 1, and for any norm on R2, delta is actually an accumulation point of the spectrum. And then 2 years ago, in 2 different papers, which are, again, in some sense, breakthrough papers by Schleichitz, he showed that for any m and n, and for the maximum norm, we have that the Dirichlet spectrum of m1 is equal to the Dirichlet spectrum of 1n. And in both cases, both, again, have the same phenomena of the spectrum being the whole segment, where in this case, in both cases, delta is equal to 1. A year ago, this was a work of myself, my master thesis. I showed that for m equals 2, n equals 1, and for the arbitrary normal R2, there exists a constant c greater than 0 such that the spectrum contains an interval of the form 0 to c, with c being optimal in many cases. And later on, just recently, Hussein, Schleichitz, and Ward essentially generalized this result to a wide range of integer pairs and a wide range of norms. And at this point, so it was, I think that everybody that was working on this object suspected that for any norm that we work, we should have this full segment behavior, as in the proofs of Schleichitz and Akhunzhanov and Shatskov. And before I move on, I also want to say that all of these works, maybe just beside this work, beside the work of Dimitri and Anurag, all of these works was in some sense technical, difficult. I don't know if difficult, but like technical and long papers. The thing that we're going to discuss ahead is more easy. And in this work and this work, there is also a calculation of the house of dimensions of matrices satisfying a specific value in the Dirichlet spectrum, which is something that we're not going to discuss. So the main result of the work of myself and Barak is the proof of this conjecture. So we prove the following. I'm going to call it in this talk theorem 1. So we need m and n to be two norms such that their maximum is greater than 1. And we take two arbitrary norms on Rm and Rn. So we have that the Dirichlet spectrum with respect to these norms and this dimension is always the full segment. Furthermore, we prove that for any c in the spectrum, the set of matrices realizing this value, meaning that they have a Dirichlet constant equal to c, is an uncountable and dense set in the space of matrices. And for the rest of the talk, what we're going to do is we're going to discuss some extensions of it. So the first extension would be changing t to the -1 to a more general function, but still staying within the realm of Diophantine approximations. I'm assuming that this sentence might be a bit vague. It will be understood in a few minutes. So we're going to have this short discussion for like 5-10 minutes. And then afterwards, we're going to have an extension to the space of lattices, where we're going to deal with the behavior of non-typical trajectories under one parameter diagonal flows. Eventually, we're also going to have like a 5-10 minutes discussion of the proof. So the first extension is something that we're going to call the gamma Dirichlet spectrum and the uniform exponent. So firstly, for gamma greater than 0, we define the gamma irrationality measure function of the space of matrices to be the same function as before. The only difference is now previously in here it was written n divided by m, which was again values that were in some sense given to us by the Dirichlet theorem. And now we change them to be some positive number. And then we do as before, we define for a fixed matrix the gamma Dirichlet constant of it to be the lim sup of the gamma irrationality measure function. And these are in some sense, as far as we know, quite, I don't know if to say new, but like definitions or objects that weren't that discussed, like investigating this kind of lim sups. I gave this talk a month ago in a different forum, and Antoine Marnat pointed out to me that he has also a paper that with notions that relates to these notions. It's not exactly the same, but this is in some sense a bit of a new thing. The thing which is not new is that for a specific matrix, we define the uniform exponent of it to be the supremum over all gammas greater than 0, such that the gamma Dirichlet constant of them is finite, meaning that this lim sup is finite, and we denote it by omega bar. So by Dirichlet theorem, we have that the uniform exponent is always at least n divided by m for any matrix. This is just Dirichlet theorem. And actually, by Davenport and Schmidt, with a little work, we know that the uniform exponent is equal to n divided by m for Lebesgue almost every matrix. So again, we have a question of what happens in the non-typical case.
Well, I think this already follows from Khintchine's proof that almost every matrix is not singular.
Mm-hmm.
So this dates back to earlier than Davenport and Schmidt, I'm sure.
Okay, thank you.
Anyway, doesn't matter.
So the question, let's fix gamma to be some number greater than n divided by m. What can we tell about matrices satisfying that their uniform exponent is equal to gamma, focusing specifically on what is the value of this lim sup? So again, we do a similar procedure as before. In order to address this question, for gamma greater than 0, we define the gamma Dirichlet spectrum to be just all values that can be obtained as gamma Dirichlet constant of a matrix, where we allow two matrices to vary in the space. And using this definition, we have what we call as theorem 2. So again, we have m and n to be two numbers such that the maximum is strictly greater than 1, and we take two arbitrary norms. And let's take gamma to be some number which is strictly greater than n divided by m, where in case n is equal to 1, we also need to assume additionally an upper bound for gamma. We need to assume that gamma is strictly smaller than 1. This is the simultaneous approximation settings. And then the gamma Dirichlet spectrum is everything between 0 and infinity. But furthermore, for any value between 0 and infinity, the set of matrices satisfying both that their uniform exponent is equal to gamma and that their gamma Dirichlet constant is equal to c is uncountable and dense in the space of matrices. And I do want to say a remark. So the remark is that we actually prove a stronger theorem for functions of the form psi of t, which are more general than the t divided by gamma case. I'm not gonna get into it because it involves, it would take me like 15 minutes more of definition, and this is in some sense, we think this is a bit of less interesting things, but those of you who might be interested in it can look at the paper. I do want to say that this relates to the settings introduced in previous works by Kleinbuch and Rao, and by Dimitri Strombergson and you. One second. So we now, in some sense, we leave the Diophantine approximation settings and we go to the space of lattices. So firstly, I need like 2 slides of definitions. I'm assuming some of the definitions will be quite familiar to you, but I'm going to do it anyway. So we let D to be, if we have two numbers m and n, we need to assume that D is their sum. And we denote with this curly xd to be the space of unimodular lattices in RD, lattices with co-volume 1. And recall that any unimodular lattice can be written as G times ZD, where G is some SLDR matrix, and that we have the identification of the space of lattices as the quotient of the homogeneous space SLDR divided by SLDZ. And now, given a matrix, we denote by lambda theta to be the unimodular lattice defined in the following way. We take IM at the left top block, we take IN at the bottom right block, and we put the matrix theta at the top right block, and we multiply this matrix with ZD. So this is a unimodular lattice. We say that two positive vectors, alpha in Rm and beta in Rm, are weights on Rd if the sum of their coordinates is both equal to 1. And we denote by M1 and N1 what we call as the standard weights on Rd. So M1 is just n divided by m times, and N1 is 1 divided by n times. Maybe I said something, maybe I confused something that I said, I'm sorry. And given two weights on Rd and given t greater than 0, we define the matrix GT alpha beta to be the diagonal matrix t to the power alpha I in the first m coordinates and t to the minus beta I in the last m coordinates. And by the fact that the vectors alpha and beta are weights on Rd, this is an SLDR matrix. This is a determinant 1 matrix. Some more definitions. So now let's assume that we have an arbitrary norm on Rd. For a lattice of covolume 1, we define Minkowski first successive minimum with respect to this norm on Rd to be the minimal value, the length of the shortest non-zero vector of the lattice. We denote the first successive minima by lambda 1. And this is again a function which is dependent on the norm on Rd that we have to keep in mind. And for epsilon greater than 0, we define k epsilon to be all of the lattices in the space such that their shortest non-zero vector has length which is at least epsilon. So here are two claims about the space of lattices. The first claim, which is in some sense similar to Dirichlet theorem, is that there exists a minimal constant. I'm going to denote this constant by R, which is dependent on the norm that we have, which is an upper value for Minkowski first successive minima, meaning the shortest vector of any lattice cannot be too long. And the second claim is that for any norm on Rd, these sets k epsilons, which are dependent on the norm that we have, if you vary epsilon to be all numbers between R and 0, not including 0, you get a decreasing exhaustion by compact sets of XD. We're going to say, I'm going to discuss formally what I mean a decreasing exhaustion by compact sets of XD if it's not understood. So I'm going to get to it in a few minutes. So with these definitions, we have that Minkowski first successive minima of a lattice is just the infimum over all epsilon, such that the lattice is not inside k epsilon. And for any matrix, we have that the lim sup of the function lambda 1 on the trajectory lambda theta with respect to the action gt alpha beta is the same as the infimum over all epsilon greater than 0, such that the trajectory leaves the compact set k epsilon and doesn't come back, anymore. Now this is a general observation that just takes the function lambda 1 and and think at it in terms of being inside sets. I want to now talk about a special case, right? So this is general for an arbitrary norm on RD and for general weights, but let's think of a special case. So let's say that we go back to the previous settings. We have two arbitrary norms on Rm and Rn, and let's denote, as the way I denoted from the beginning, the norm on RD defined in the following way. You take a vector in RD, you write it like this, and you take the maximum between the length of the first m coordinates with respect to the norm that you have in Rm and the maximum of the last n coordinates of the norm that you have in Rn. So here is a small claim. So let's say that we have two arbitrary norms on Rm and Rn, and let delta be the minimal constant which satisfies Dirichlet's theorem that we had before in the beginning of the talk. And now let R be the minimal upper bound of lambda 1 with respect to this norm on RD. Then these constants are essentially the same up to some scalings of the dimensions. And for any matrix, we have that the lim sup of lambda 1 of the trajectory lambda theta for the standard weights. These are not the general weights, not arbitrary weights, but the standard weights is the same as the Dirichlet constant of the matrix theta, again up to some scalings which are dependent on the dimension. So if we have this claim, let's think of theorem 1, the big theorem that we had before, just in terms of the space of lattices. So what is theorem 1 in the space of in the language of lattices? It is the following. Again, we have m and n to be two numbers such as their maximum is greater than 1. We have two norms on Rm and Rn, and let R be the minimal upper bound of lambda 1 with respect to the norm on RD, which is the maximum between the two norms. Then for every C between 0 and R, there exist uncountably and dense many matrices corresponding to unimodular lattices of the form lambda theta, such that C is the infimum over all epsilon, such that the trajectory of lambda theta with respect to the standard weights leaves k epsilon for all t large enough. Now, I'm assuming that maybe this theorem, maybe the algebra of it is not completely understood, but the best way to think of this theorem is just with a picture, because the heuristics of it is very, very, very understandable. So I draw the space of lattices like this, right? Because we want to say that it is not compact, but that the Haar measure of it is a probability measure. And we have the set KR. KR, we draw it like this because it is small in the sense that it has an empty interior. And now let's think of C being some number which is strictly smaller than R. So KC is all of it's also the interior, right? It's all of the set, not only the curve, but everything which is in here. And what the theory tells you, the theorem tells you is that you can find a lattice. The lattice will be of the form lambda theta, such that when you start to act on it with this action, you get that eventually at some point, here's the point, you leave this KC set, but you're going to come infinitely many times, infinitely often, infinitely close to the boundary of this set, KC. And you can do it to any C which is between 0 and R. And the idea from now on is essentially generalizing just this picture. Okay, so this picture is very specific. It's specific because these k epsilons are for the specific norm of this norm on RD, the maximum between two norms on Rm and Rn. And this weights are specific, and we wanna generalize it to just arbitrary sets and arbitrary weights. So the motivation is to extend to arbitrary norms on RD and to arbitrary weights. This is the first thing. And then extend to sets which exhaust the space of XD, which are not of the form K epsilon from some norm on RD. So in order to address these questions, we have some new definitions. So take B to be some number which is strictly greater than 0, but B can also be infinity. And let's take a collection of subsets of XD, where we parameterize them with epsilon. So given this collection of sets, we say that they are a continuous decrease in exhaustions of the space of lattices, of unimodular lattices by compact sets, if we have the following. Firstly, we have that E epsilon is compact for any epsilon. Secondly, we have that this is continuous, just in terms of sets. Thirdly, we have that the interior is non-empty for any epsilon strictly smaller than B, but the interior at the end is empty. The interior of EB is empty. We have that this is an exhaustion, meaning that any compact sets, any compact subset of XD is contained in E epsilon for some epsilon. And we have that the map that takes a lattice and sends it to the infimum over all epsilon such that the lattice is not inside the epsilon is a continuous function. And I just want to remind you that this is, for the specific settings that we had before, this is just lambda 1. This is Minkowski first successive minimum, which is a continuous function. So we generalized it to now a setting which is not being related, which is not connected to the lambda 1 function. And firstly, if this is not understood, please, again, I say, feel free to stop me and ask question, but what you should have in mind is just the picture from before. The picture from before is in some sense, again, you have some K, now it will be EB, not KR, some kind of a small set, and then you continuously start to inflate the sets with compact sets that exhaust the space. So the two main examples that you should have in mind is firstly those K epsilon sets for any arbitrary norm on RD, not necessarily one that comes from two maximum norms on Rm and Rn, can be any norm on RD. And another good example to have in mind is, let's say that you have a metric on XD, let's denote it by rho. And let's say that you have a specific lattice, let's call it lambda 0. So we denote in the usual way the closed ball with respect to this metric rho around lambda 0 of radius epsilon, with the convention that the closed ball with radius 0 is the singleton, it's not the empty set. Then if rho is a proper metric, meaning closed balls are compact, then this collection, where now epsilon varies between infinity and 0, is a continuous increasing exhaustion by compact set of XD. I haven't defined in here what does it mean to be increasing, and we also do not define it in the paper, but it is obvious. So in here you have the opposite. In here you have that the map needs, instead of sending it to the infimum, you need to send it to the supremum. And in here you just change the 0 and the B rows. But again, just keep in mind the picture. Leave the algebra outside and keep in mind the picture.
Excuse me, but when you say increasing, does it mean strictly increasing or not strictly sometimes?
So
so what do you know about the complement?
I mean, in here we've defined it as strictly increasing.
Where?
Here. I mean, in here strictly decreasing.
So,
and
wait, so this inclusion means a proper subset?
Yes. But I actually, I can think like the idea is that this is a very strong requirement. So I'm assuming, I haven't thought about it, but I'm assuming that if you change it to a weaker inclusion, but you still ask this to be continuous, then still the theorem that I'm going to discuss in a minute still would hold. But
Okay.
I don't want to say that I haven't thought about it.
Okay.
So now let's assume that we have a continuous decrease in exhaustion of XD by complex sets. So this is the picture of it. EB is some kind of a small set. E epsilons are some sets that go big and fill the space. And let's assume that we have two arbitrary weights on RD. Then for a unimodular lattice, we define the extended Dirichlet constant of it with respect to this exhaustion of the space and with respect to the weights alpha and beta to be the infimum over all epsilon greater than 0, such that the trajectory of the lattice lambda with respect to the weights alpha beta eventually leaves E epsilon. Okay, so this is a generalization of what we previously had for the specific case that we previously discussed. And now let's define the extended Dirichlet spectrum now of the space of lattices, which is going to be something which is dependent on these sets, the epsilons and the weights alpha and beta, to be just all values that can be obtained as Dirichlet constants, as extended Dirichlet constants, where you allow yourself to vary any lattice that you want. So now here's theorem 3. So let D be a number which is greater or equal than 3, and we let E epsilon to be any continuous decrease in exhaustion by complex sets of the space of unimodular lattices for some B. It can be any number between 0 and infinity, including infinity. And let M and N be two numbers such that their sum is equal to D. And let alpha and beta be arbitrary weights with respect to these dimensions. Then the extended Dirichlet spectrum is always everything between 0 and B. And furthermore, for any C within the spectrum, the set of matrices satisfying that the Dirichlet constant of the lattice lambda theta equal to C is uncountable and dense in the space of lattices. And now a small question is what happens in the D equals to 2 case, and why this is an interesting question, because in the previous definitions, in the Diophantine approximations definitions, we had that the 1-1 case, the Dirichlet spectrum was not 0-1, but in the way that we define the extended Dirichlet spectrum in the space of lattices, we also allow arbitrary lattices which are not of the form lambda theta for some theta a real number. Then this question is an interesting question, but you can easily prove this is a small theorem that for the D equals 2 case you cannot do the same thing. So what does it mean? Let D be the number 2, and let E epsilon be any continuous decrease in exhaustion by complex sets of X2. Then the extended Dirichlet spectrum of the D equals 2 case is not 0 to B. And furthermore, there always exists some R such that the segment between 0 and R is completely outside of this spectrum. Meaning that we also have, in some sense, a generalization of what happens in the Diophantine approximation settings to a more general settings which are not essentially related to Diophantine approximations.
Sorry. So
Yes.
can you comment on the last claim?
Mhm.
Wait a second. Okay. B. I forgot which way the inclusion goes. EB is the smallest one.
Yes, EB is the smallest one.
Or EB is the smallest one. Okay.
Yes. I think the best thing actually is to think about it
Okay.
heuristically.
Yeah. Then of course.
So heuristically, what happens in the
Yeah.
x2
Then
case?
it's just the same statement as before.
Yes. So you have two behaviors in some sense. You as a divergent trajectories. The Dirichlet constant of them for any epsilon would be 0, or that you have some kind of a ER that any trajectory is going to come back to it infinitely many times. So it's going to have some values which is at least R, a Dirichlet constant which is at least R.
Mhm. But you do you know anything about values close to B?
No, we haven't thought about it. We haven't discussed it.
Probably, I mean, if you take a sequence of like in your example with balls,
Mm-hmm.
you take a family of balls centered at some point,
Mm-hmm.
then probably your Dirichlet spectrum should contain the interval from B to B minus epsilon.
Yes,
Unless at least for some centers, not
yes,
not for all
yes.
centers, but for some centers.
I would say that I'm assuming that for some centers there will be an epsilon such that there will be a segment in it. But if you think about it in terms of the Diophantine approximation behavior, in the 1-1 Diophantine approximation settings, the Dirichlet spectrum is chaotic. It's not that you have, it's not
But
like that.
yes, but this is because this set EB that you zoom in actually consists of divergent trajectories. If you
Um,
if you
um, I don't know to say.
okay, maybe
Yeah,
we can. So all I was asking is whether or not you can prove something general for values of this spectrum for d equal to 2 and
no,
say for the family of balls.
no. So I'll just I want to have this theorem in the slide. So I'll say no. We don't know what's going on beside of it, but for the case of for the specific case where you generalize, for the specific case of the Diophantine approximation settings, this is very, very well studied by continued fractions. So it's only interesting when you look at some weird epsilons for some sense. Balls, for example, what you suggested.
Yes. Okay.
So for the next 5-10 minutes, I'm going to have a short discussion about the proof. The proof actually is, this is now, I'm going to go back to the beginning. It's not difficult. It's quite understandable. I'll discuss the essence of it. So firstly, for a matrix theta and for t greater than 0, let's just define f of theta t to be the infimum overall epsilon such that the trajectory, not the trajectory, I'm sorry, the value at a specific time and specific matrix is outside of E epsilon. This is just lambda 1 for the specific settings that we started with. So we have that the extended Dirichlet constant of the lattice lambda theta is the lim sup of this function f.
After some normalization, right? You had these exponents m over m plus n or something.
No, so the extended Dirichlet concept. This is right.
Right. You have extended one. Okay.
Yeah, you're right. You're right. We denote it in the similar way, but this is something of lattices, not something of matrices.
Okay, fine.
So now essentially, what we want to prove is that we want to prove that for every C between 0 and B, there exists a matrix such that the lim sup of this function is equal to C. And what's the basic ingredients for us to do it? Firstly, is we have that f is continuous on both variables. This was the strong requirement that we had on those sets E epsilons, where we asked it to be a continuous decreasing exhaustion, and the fact that this is a continuous action. Secondly, we have the typical case, the Lebesgue almost every behavior. This lim sup is actually B. This is in some sense just saying that this trajectory for Lebesgue almost every matrix is dense. Okay, this is done by work, a recent modification of a work of Dimitri and Anurag Rao, of an old work of Dimitri and Barak. Okay,
right.
But
it's just ergodicity. Oh no, not just ergodicity.
Yes, not just ergodicity.
Right, equidistribution of translates of this.
Yes.
Okay.
But we don't even need this. We just need to know that the set of matrices satisfying that this lim sup is equal to B, to the upper value of the function, is dense. This is all we need to know. And the third requirement, which is in some sense the difficult thing, is we need to know something about the set of matrices satisfying that the lim sup is equal to 0. We need to know that this set is rich. And I don't want to get too much into it, but without being too accurate, we need to know that a significant part of it is path connected and dense. I'm going to discuss this in the next slide a bit more. And I just want to recall that saying that this lim sup is 0 is the same as just saying that this trajectory diverges in the space. So we need to know something good about divergent trajectories. And once we have these three ingredients, which are completely topological, we just use these facts in order to modify a very famous construction by Khintchine. This construction of Khintchine was originally in 1926. Since then, I think it appeared in like, I don't know, 5-6 papers that everybody did like some small generalization of it for some specific use. And we did some kind of a modification of an old modification that Barak did 20 years ago in order to prove that any scene here can be obtained as a lim sup in here, but this is essentially just a topological theorem. So the next thing that I want to discuss is only just a small discussion about these sets. So what are these sets? What do we take? So we need to split between the cases of n equals to 1 and n greater than 2. So for n equals to 1, this is the simultaneous approximations settings. So for I and z rational vectors, we define xIz to be the line defined in the following way. It's just you take the line with a slope of vector I, and you look at this shift with vector z, and you just think about all of these lines. Okay, and you need to just imagine it. Let's say, for example, in the plane, you just have many lines that they are dense, right? They contain all of the rational vectors, and they intersect each other infinitely many times and in a dense way. This is in some sense the rich image that you should have in mind. For the case that n is greater than 2, we need to have a small small different constructions. So again, for I in Qn and Z in Qm, we define Xiz to be the n minus one dimensional affine plane, defined in the following way. We take all of the matrices that satisfies this equation. And now the heuristics of it is a bit less obvious, but you just have many planes, affine planes that they are dense and they intersect each other all over the space in some sense. And in both cases, for any I and any Z and any matrix on this set Xiz, we have that the lattice lambda theta is a divergent lattice. We actually know something more. I haven't written it, but I'll say it. We also have a very good control of the rate of escape, the rate of divergency on each line. This is also, in some sense, an important ingredient for us. And now going back to the case of d equal 2, you can ask what in our, I mean, we knew that our methods are not going to work for the d equals 2 case, but you can ask why. So in the case of d equals to 2, we only have the standard weights alpha and beta are equal to 1. Being a divergent trajectory of the form lambda theta only happens if theta is a rational number, and the rationals are not rich enough for our argument. They're not, they are isolated from each other. We do not have this image of lines that or connected objects that intersect each other. So if you have any questions, I'll be happy to answer it. And thank you very much for listening.
Okay, well, let's thank Alon. First, that was an interesting talk, but maybe since we have some time, can you go back to the
yes
to the slide? And I mean, you listed the
what slide do you want me to go back?
No, it's okay. Just look at this. So you define this guy.
Yes.
So what do you do with these guys? You need to construct a trajectory using them.
So I'll go even one slide before. So the proof is a proof by induction. So it's a bit difficult to understand. I mean, I don't know how to explain it in like 5-10 minutes, the inductive procedure. It's not that simple.
Well, let me try to explain the proof. Maybe you tell me that I'm wrong. So you want to have a trajectory which goes pretty close to some compact set, and it doesn't go close to a smaller compact set. That's what you want. All right. So I guess what you need to do is you need to approach this compact set, and then using this axis that you showed, this resonance sets consisting of divergent trajectories, you want them to, so you find the point of this x, one of these axes close, and you follow it, and then the trajectory will go very far away. But then that's the only way I can think of that you're using this axis. So you're saying that you're using this divergent, the sets with divergent trajectories and divergent fast. So apparently they should move your trajectory fast, but then it should come back to this set again. And somehow you should make sure that it doesn't go deeper in this set. So this I don't understand how you do it.
Yes, so everything you said is correct. It's just that, as you said, I don't know if it gives the idea of the proof. And in order to understand it better,
we need
I mean, it's a bit. I'll try to say something verbally. I don't know if it will be understandable, but you should think of an inductive procedure, and let's say that you're at the case step of the inductive procedure, and you're inside some kind of a ball. Yes. So you know that, and you have in this inductive procedure, you also inductively construct the times. you're not only inductive, you have an inductive procedure of knowing what happens at segments of times. So you use this to know that inside this ball, you must have a matrix such that it's gonna get, you can get at any time greater that you want, any value which is closest to B as you want.
Yes.
So this is in some sense, inside this small ball, you have one point that in faraway times, you can have very big values. And on the other end, you have a line inside this ball that you inductively kept in the inductive procedure, that along this line, you know that everything is very, very, very small and you control the times of it really, really good.
Yes.
Then, and this is in some sense, this is a bit different than what Khintchine did. He looked at a bit different things, but this is very, very similar to what Khintchine did, these observations of these lines that you can control very, very good. And then you need to do some kind of a nice trick of path connectedness, of thinking of, you have a line, you have a point, which they behave very, very differently. But this point, you have another line that's going to intersect, that it's going to come very, very close to it, because the fact that these lines are dense. So you're going to have essentially, in some sense, two lines with some kind of a different behavior, and you use this path connectedness behavior and to get some kind of a topological argument. I do want to say, I mean, I don't know if it will happen or not. I might give a short talk of this paper in the seminar in York. If I'll do so,
Okay,
then
I hope to be there. So
if I'll do so, it will be a short talk that I think I'll only discuss the proof, because I gave already this talk in many places, and I'll give like a short discussion of just a specific a specific case of discussing the proof.
okay, any other questions?
Can I ask a question?
Mm-hmm.
So in your construction before, you had this KB, and you said the interior of KB should be empty. So where
Mm-hmm.
exactly do you use it?
That's a good question. We use it just in some sense to get a theory which is the most interesting that you get. I mean, I'll go back in the picture. So if you're saying, okay, let's not ask for EB to be with a non-empty interior, then in some sense, our theory would not tell you what happens inside EB. And if you're not asking it to be with an empty interior, then it can be a big set. So think that, let's say now EB is this E epsilon. It's a big set. So our theory will indeed, it will work. It will tell you, yes, the spectrum that you're going to define will be everything, but in some sense, not knowing that the set at the end as an empty interior is in some sense not knowing what happens inside the set. So we thought that aesthetically, this is the most interesting or beautiful way to present it. But you're right that you can also ask it not to be empty. I don't know if it answers your question.
No, thanks. Yeah, yeah, I was just wondering, maybe in some other settings, it could be that you don't get the interior to be empty.
Then if you'll have like a specific setting that you're interested in, I'm assuming that our methods will work with a very small modification, like with probably nothing.
But you don't need, you don't use the condition
No,
that has
no,
empty interior.
no.
So you can just throw it away and nothing will.
Yes, yes.
Uh,
That's probably what JS wanted to say.
Mhm.
Mhm.
Thank you.
Okay. So yeah, let me ask strange question. I don't know if you thought about it or not. Can anybody say anything about the restriction of Dirichlet spectrum to badly approximable matrices? In other words, suppose you want to consider orbits which have this behavior, which enter E epsilon but don't enter anything smaller, and at the same time they are bounded. So
Yes.
only bounded orbits. Then I suppose that your methods will not work because whatever orbits you construct that attain this Dirichlet constant, they are unbounded, right?
Yes, you're right. We will not know. Our construction will the inductive procedure will give you an upper bound of this value, but you do not know a lower bound, and our method, I don't think there's any way of modifying to modify.
Probably the lower bound is 0 because you.
Yes. I mean, you don't know when the typical behavior is that it will be 0. Our method just you don't know.
Okay. Maybe you're right. Maybe you don't.
I mean, I'll go back like to this picture. Our method just tells you like, okay, at some point you leave the set, you're gonna come infinitely many times close, but you don't know, maybe like at some point you go really far away and then you come back. And then you go really, really far away and then you come back. Knowing that it is also badly approximate, meaning that like you also have some kind of a setting here that you cannot go outside of it.
Okay, so this you don't know.
No. And maybe for people in the audience that are not familiar with it, there is one work of Nikolai Moshevitin and Akhunzhanov where they do ask this question for this, not for the space of lattices, but for the Diophantine approximations case of realizing value of the Dirichlet spectrum by badly approximable vectors.
But they have some results, or they only?
Yes, they have a result for the simultaneous approximation case for dimension 2, where they show that the spectrum, that the badly approximable, if you look at values fulfilled in the spectrum by badly approximable numbers, vectors, then this is dense in the spectrum.
Okay, yeah, it seems to be natural to conjecture such a thing in your general setup. Okay, other questions, comments? Okay, great. So let's thank Alon again for a great talk. This was very interesting. Everybody should read the paper.
Thank you.
And we finish, and hopefully we'll meet at some point in a few weeks, to be determined. Please watch the news.